Thank you, Dr. Lee, for the very kind introduction. Good morning, good afternoon, good evening, everyone, depending on where you're joining from. I'm very happy to be here and share some thoughts on the emerging research needs and what we can do to decarbonize primarily water. And then I'll talk a little bit about what we're doing in the energy space. And I'll focus on the role of materials. So just to start us off, some very high level motivation. If we look at the energy demand, we can see this is just electricity demand. It's increasing over the next few decades as we expect. But what's interesting to note is that it's still going to be primarily fossil fuel dominated. So the share of renewables is still small. So there's a lot we need to continue to do on decarbonizing the energy part. But what I want to focus on is also the water aspect. So here, if we look at by the end of this decade, so by 2030, the global population will increase, and about half of that population is going to experience severe water stress. What that means is that the existing freshwater reserves, which naturally renew with rainfall or snowmelt, those resources are being significantly depleted. And more than half the world's population will face this water stress. Now, it's not that there is a shortage of energy or water, right? We're using our annual energy use is a very, very small fraction of the solar energy that's available. And similarly, even our annual water consumption is much less than 1% of the water resources on the planet. But the challenge is that we need to be able to take energy and water in its existing form and convert it into forms that we can use it, and doing this in a way that's sustainable and affordable for the population. Now, when we talk about water, it's easy to think about potable water use, so for our consumption, but actually the biggest sources of our consumers of water are different sectors of the economy. So water is a critical resource for oil and gas production. So typically every barrel of oil that's produced requires about 10 barrels of oil, 10 barrels of water in order to produce that much oil. So significant amounts of water are consumed in the process, and also a lot of water is generated as waste at the end of the process. Similarly, water is also widely used in cooling our thermoelectric power plants. And so if we don't have access to water, that would really threaten our energy supply. And water, of course, is a critical resource in manufacturing, as well as in extractive industries, mining, for example, lithium mining as well. And so recognizing, this importance of water, especially in the energy sector, I like this quote from JFK, who said that anyone who can solve these problems of water is worthy of 2 Nobel Prizes, one for peace, because this is such a critical resource, and then one for science, because this is a really challenging technology. So the good news is that the Department of Energy has recognized this importance of securing water supplies so that we are able to handle the water stress. And so recently, in the last 3 or 4 years, there has been a lot of funding that's come out of the DOE on trying to design next generation desalination technologies to increase our freshwater reserves. So let's look at what the water map really looks like currently. So if you start with fresh water at a source, most of that fresh water you can see is being consumed either in the agricultural sector or for our power plants, so energy generation. Those are the 2 main consumers of water. After agriculture, a significant amount of the water is consumed and only a small amount is discharged. Whereas what we see with a lot of the energy sector is the water, primarily over like 70% of the water that's used is just discharged. So what we're interested in is going from this very linear model where we take the water and then discharge it as wastewater, instead reuse and recycle that wastewater using desalination technology so that we can get to a circular water economy. And the way we do this is with desalination technologies. And desalination is a multi-step process, and each step in the process requires energy because you are trying to separate salts or other contaminants from the water. And so typically what it looks like is you would start with a pre-treatment, which is just a filtration or any kind of sedimentation process, after which the wastewater would go through a reverse osmosis membrane process. So here you're applying electricity to force water across a semi-permeable membrane that blocks the salt. Reverse osmosis, because of the pressures that the membranes can withstand, can only recover about 50% of the water. So you're left with what's called a brine, which now has twice the salt concentration because we've removed water from it. This brine can then be treated using a thermal desalination process. So you can use a brine concentrator, which essentially will evaporate the remaining amount of water. And then finally, you can send it into a crystallizer where you saturate the solution all the way up till the solids precipitate out. As you can imagine, this process is very, very energy intensive. And that's why getting to zero liquid discharge, where you extract all the water, is not employed widely because the process is so energy intensive. So an alternative to doing zero liquid discharge with desalination technologies is to just use natural sunlight to evaporate the wastewater. And so you can see a lot of examples of evaporation ponds used with industrial processes in order to evaporate the wastewater just under natural sunlight. This, again, is just showing you the specific energy consumption of the different types of desalination technologies as a function of salinity. As expected, as you go higher up in salt concentration, the energy required for that separation increases significantly. I want you to remember that one number to keep in mind is that if we're starting with a source that's about 3.5 weight% of salt in water, the energy required is on the order of 1 kilowatt-hour per cubic meter to do the separation. Whereas currently the amount of energy that we use, as you can see here, can be significantly higher. So there is a lot of opportunity to reduce energy use in the water treatment or desalination industry, and also think of ways to decarbonize it, because currently 99% of desalination plants are driven by fossil fuels. And so this has really brought a lot of focus on how can we do solar desalination, and not really at these lower concentrations, but up here where the energy penalty is very, very large. So how can we do solar desalination for zero liquid discharge? So as I mentioned to you, we can use just evaporation ponds where the water from thermoelectric power plant, the cooling tower blowdown, or lithium mining, or oil and gas produced water is just left in a man-made pond and allowed to evaporate under natural sunlight over time. The issue with this is that water is not a good absorber of solar energy. So as a result, it can take anywhere between 12 to 18 months to evaporate the water that's produced. So it's a very, very slow process and also requires very large areas of land. So what materials can do here is we can actually use specific types of materials to localize heat at the interface where evaporation takes place, so at the surface of the water rather than heating the whole bulk. And so a lot of literature recently in the last about 5 years has focused on developing these photothermal converters. So these are now materials that will take in sunlight, convert it into thermal energy, and localize that thermal energy at the surface of the water so that you can get much higher evaporation rates. So a typical photothermal converter comprises of a solar absorber, which is porous, so that the water can come up to the surface. There is then an insulating foam to separate that top layer of water from the bulk water. And then finally, there is a hydrophilic wick, which is going to transport water from the bulk to the surface. So with this combination of different materials, you can essentially create a very localized heating at the surface, which can also allow you to generate steam. So solar steam generation, because you can get to very high temperatures just under natural sunlight. And you can see these are some different examples of materials that have been used. So carbon foam or graphene oxide, leaf. In all these cases, the main thing is that it's a porous material that has a very high solar absorption. So typically a lot of black materials. And the effect here is interfacial heating, where you're localizing heat at the surface so that your bulk still remains close to ambient temperature, while your surface temperature increases by heating under sunlight, and you can increase evaporation rates. So a lot of work has been done in the space, but when we think about using this for desalination where salts are involved, oftentimes what you will see is that the salts begin to precipitate all over the porous structure and within the pores of the structure. So over time, if you're running this for several days, you end up clogging your entire porous solar absorber, as a result of which your evaporation rates will significantly drop over time. So what we were interested in doing is, can we get the same kind of heat localization, but without actually having the water come in contact with the photothermal structure? So here we can really leverage the inherent absorption properties of water. So here I'm showing you a typical evaporation pond. Normally when the sunlight comes in, there is a little bit of evaporation from the surface, because really you're heating up the entire volume, because water is fairly transparent at solar wavelengths. So this is shown here. This is the absorption coefficient of water as a function of different wavelengths. And you can see at solar wavelengths, the solar spectrum right around here, 500 nanometers or so, the penetration depth in water is close to a few hundred meters. So you would need a very large depth of water to absorb all the energy. Whereas if we look in the infrared, the absorption coefficient of water increases by several orders of magnitude. And as a result, most of the energy in the infrared can be localized within just a few microns thick layer of water. And so really what we can do is convert the solar spectrum into wavelengths concentrated in the mid-infrared, and that would then allow us to localize heat at the surface for evaporation. So we do this with a 2-layer photothermal converter, where the top layer consists of a selective solar absorber, which has a very high absorptivity at solar wavelengths and very low emissivity. And as that solar absorber heats up, it is attached to an infrared emitter. And as a result of the infrared emitter heating up to temperatures above 70 degrees Celsius, it'll start emitting in the infrared wavelengths. And because water is a very strong absorber at the infrared wavelengths, that energy is concentrated or localized at the surface, resulting in a temperature rise at the surface for evaporation. So we convert solar wavelengths into primarily the infrared, close to around 10 microns. And so we demonstrated this at the lab scale. Again, you can see that the absorber and emitter is physically separated from the water, so there's no contact at all. And under a solar simulator, as soon as the sunlight is incident on the absorber surface, within a few minutes, the absorber temperature increases to about 70 degrees Celsius. This is under one sun. And if we track the temperature of the water under these conditions, we see that the temperature of the surface starts increasing, whereas the bulk temperature or the rest of the water remains fairly close to the ambient temperature itself. And here from the infrared image, again, you can see that the heat is really localized at the surface. And so this radiative heat localization, completely non-contact, just radiation, thermal radiation, gives us a 20 degrees Celsius increase in the surface temperature compared to the bulk temperature. So as a result, the evaporation also increases. And here you can see just evaporation under dark conditions in the black curve. Under a solar simulator at one sun, the evaporation rate increases. But once we add this photothermal umbrella, we see a significant enhancement in the evaporation rate because the surface temperature is that much higher. And if we let this process continue, at some point you can evaporate all the liquid and you're left with salts that precipitate on the sides of the container. And this allows us to reach zero liquid discharge conditions without any challenges related to clogging because it's completely non-contact. So we also designed a COMSOL model to verify and predict the overall performance. And again, as you can see, we're getting heat localization at the surface. And we can divide the total conversion efficiency from sunlight to the amount of water that is evaporated by looking at 3 different efficiencies of the materials involved. So the first is the efficiency of the absorber itself. So this is directly related to the optical properties of the absorber, which is taking in the sunlight and converting it into heat. And here, because of the optical properties of our absorber, we get a very high efficiency. Next, we have the radiative coupling between the infrared emitter and the surface of the water. So how well that energy is transferred to the surface of the water. And here, the view factor for radiation becomes a very important parameter. So there is some room for improvement for this particular efficiency. And then the final one is from all the energy that's absorbed by the water surface, how much of that is actually used for evaporation. And here we see it's only about 60% because there are other modes in mainly conduction to the bulk of the water as well as other heat losses. And so there's a lot more that can be done over here. Overall, we achieve about a 43% efficiency, which from the models can be increased to about 68% with further thermal design. But beyond 68%, we cannot really go with this particular type of design. And mainly here, we're really limited by the amount of energy that is required to evaporate water because the latent heat of vaporization is very, very high. And so we're also looking at using processes that are not evaporative in nature. And so here we can look at a combination of a membrane and a thermal process. So just as benchmark, the enthalpy of vaporization for water is about 600 kilowatt hours per cubic meter. You can recycle this, so you can get this down to maybe about 60 or 80 kilowatt hours per cubic meter with recovering the heat from condensation. But the energy required for separation of salt from water, so the minimum energy, the Gibbs free energy, is only on the order of 1 to 10 kilowatt hours per cubic meter. So there's a big difference or big gap that we need to bridge. So we have been working on this membrane and thermal hybrid process. So we start with a membrane process. You have your wastewater or your feed on one side, a semi-permeable membrane in between, and then you have what is called a draw solution. This draw solution has a concentration which is higher than the feed solution, and as a result, you can draw water across the membrane without applying any external energy input. So once the draw is diluted, you still have to obtain clean water. So we send it through a thermal separation unit where solar energy is used to separate the draw from the water. Now, what I want to point out is that we're not using evaporation here. Instead, the draw solutions that we use are ionic liquids. And these particular ionic liquids have a very interesting phase behavior with water shown with this phase diagram. So essentially at certain temperatures and concentrations, the water and ionic liquid form a single fully mixed phase. Once you heat it up above a critical temperature, the ionic liquid and water separate into 2 different layers, as you can see here. And the temperatures you require for this process are fairly small. So going from about 30 degrees to 35 degrees will give you phase separation. And this is completely a liquid-liquid phase separation. So we're able to move away from the amount of energy required to evaporate water by doing a liquid-liquid phase separation that has a much lower enthalpy. So these types of ionic liquids exhibiting this behavior in water are referred to as lower critical solution temperature materials that we use. And this overall process is forward osmosis with solar thermal regeneration of the ionic liquid. So these are just some chemical structures of the ionic liquids comprising an organic cation and anion. One of them is hydrophobic, one is hydrophilic, and that balance of hydrophobicity and philicity is what gives us this temperature-dependent phase separation. When the ionic liquids are dissolved or mixed in water, they exhibit an osmotic strength because the ions are mobile. And so depending on the concentration, the osmotic strength of these mixtures can vary. So if we're working with brackish water desalination or oil and gas produced water desalination, we can pick a different concentration of the ionic liquid to start with. And then characterizing the phase diagram of the two ionic liquids that we've chosen, and you can see the LCST is fairly low, around 30 to 40 degrees Celsius, but the separation gets better as we go to higher temperatures. So really we want to try and be around 50 degrees Celsius in order to get a better separation of water and ionic liquid. So we tested this at the lab scale. This is just the forward osmosis part of the system. And we used produced water from oil and gas extraction from an oil field in Southern California. So these are two different fields that we got the produced water from. As you can see in this inset image, there's the color of that water contains a lot of suspended solids as well as several dissolved solids, including salts and some heavy metals. We demonstrated that you can successfully desalinate this oil and gas produced water using these ionic liquids. And then once you get your diluted draw solution, again, we can use our photothermal absorber in order to start heating up the mixture. And here I'm showing you the increase in the temperature of the ionic liquid water mixture over time under sunlight. And this video just shows you the actual phase separation. So you can see as we heat it, the ionic liquid and water start mixing into this very milky type of mixture. And as we cool it, you can see that it's separating into two layers with the ionic liquid settling at the bottom because it's a little bit denser. So we match the emission from the infrared to the absorption spectrum of the ionic liquids, which also happens to be in the infrared because of the chemical functional groups in these materials. And this is just an NMR figure that's showing you essentially that our top layer is 90% water or about 92% water, indicating that most of the ionic liquid has been separated. This residual amount of ionic liquid can then be completely rejected using a nanofiltration membrane. So we can get ultra pure water from this process with a post-treatment. So excitingly, we're working on scaling this up. So currently, everything I showed you was at the lab scale, and currently we're working towards developing 100 cubic meters per day pilot plant. This is as part of the Department of Energy Solar Desalination Prize. And we're working with Porifera, which is the membrane manufacturer, as well as Lawrence Berkeley National Lab to scale up the synthesis of the ionic liquids and coupling that with solar thermal collectors from Arctic Solar. And so within the next year, we'll be designing this pilot scale plant for testing. So shifting gears just a little bit, I wanted to touch on opportunities in the energy space and some of the work that we're doing there. So everything I discussed till now was on desalination and water treatment. But if we really want to transition to a clean energy future, we also really need to decarbonize our buildings. And if we look at energy use within a building, so this is from 2020, we can see that over 60% of that energy is in the form of heat. So that's space heating as well as hot water. And then some other energy is really for air conditioning, so cooling. And so we've been looking at doing solar energy storage, thermal energy storage, for buildings using salt hydrate materials. So these are materials which undergo a reversible endothermic exothermic chemical reaction. And in that process, we can store heat during the day and release it at night when it's required, for example. And so these salt hydrates undergo just a hydration-dehydration reaction, which we can then leverage for thermal energy storage to match energy demand with the supply. These are much more interesting than just hot water storage or phase change or latent heat storage because the energy densities can be an order of magnitude higher. And so we can get very compact thermochemical energy storage, which is important for building applications. There's a lot of work to be done on making sure these reactions are reversible in practical use. And so we're focusing on making sure that they have the right hygrothermal stability. And then finally, one other thing we can do for more on the personal cooling side or wearable electronic side is we can use thermoelectric generators or Peltier coolers in order to reduce energy consumption by tailoring the environment around an individual. So what we've done is we're working with polymeric and hybrid organic and inorganic materials. We've been able to screen print thousands of these thermoelectric legs onto fabrics or textiles in order to do body heat harvesting or personal cooling, and also designing flexible heat sinks that can be attached to these devices. As you can see here, 3D printed flexible heat sink to attach to textile-based devices so that you can do localized cooling on the individual rather than doing space heating and cooling. So those are just a couple of things we're doing in the energy space. So with that, I will wrap up. And essentially, I discussed how materials can enable significant advancements in energy and water technologies. And this can really span everything from fundamentally understanding the materials all the way up to applying them in systems to produce clean energy or clean water. So the past was a lot of large-scale static energy water systems, whereas with materials now we can enable efficient and dynamic systems using these types of smart materials. And with that, I just want to acknowledge my lab as well as collaborators at Lawrence Berkeley National Lab. Thank you, and I'll be happy to take any questions.
Thanks, Akanksha, for the great talk. I see a question from Ju.
Hi, Akanksha. This is a super innovative and creative work, actually multiple work. On the kind of down conversion, my understanding is you first absorb the visible spectrum, and then you use an emitter to re-emit into 10 micron wavelengths infrared.
Right.
So are there, are there other ways instead of, like, what kind of temperature is this umbrella at, for example?
Yeah, so this really depends on how well you limit convection from the top surface. So in our case, without a convection shield, we can only get to about 70 degrees Celsius. But if you can really limit convection on the top surface of your absorber, our models show that we could, this absorber temperature can go up to 150 degrees Celsius.
So is there any like direct conversion where you can, change one visible photon into 10 infrared photons, for example, with some nonlinear photonic process. I mean, what kind of ideal efficiency would you get? You mentioned, I think, something like 40%. So is that the best one can do?
No, so the 40% is going from the sunlight all the way to how much water is evaporated, right? But but if we're looking at only the photothermal efficiency itself, that is about 91% that we can get.
And that's achieved by 150 Celsius coupled to an infrared emitter?
That's right, yes. And in this case, so this is just a black body emitter. So if it's a black body emitter, again, you're not emitting just at the 10 microns, it's over, several wavelengths. But if you can make a selective emitter that's emitting just at the 10 microns, that would couple a lot better with the water and also much better with the ionic liquid wavelengths. But in this case, it's just a black body emitter.
That's very interesting. And 91% is really high. Okay, and then on your second work on using the kind of inverse phase separation, spinodal decomposition, this I mean, even if you raise temperature, my understanding is there's still some ionic liquid in the water phase. So
that's correct.
How are you going to retrieve it out eventually?
Yeah, no, that's a great question. So what I'm showing here from this NMR data, what we see is our top layer has only about 90% water. So it's not 100% water, right? So there is about 8 to 10% by weight ionic liquid that's still in the heated water layer. So the only way we can now remove it, so we cannot do a thermal separation anymore because we're basically hitting the ends of that phase diagram. So for this, what we do is we do a nanofiltration post-processing. So nanofiltration is able to completely reject the residual ionic liquid because of the size of these molecules. So if you apply, we've done some lab scale experiments with a pressure of about 8 bars and a commercially available nanofiltration membrane from Dow, we can get 100% water in that phase and complete rejection of the ionic liquids.
Gotcha, and that's sort of like a size effect. So the energy cost is not okay.
Yeah.
Fantastic. Thank you.
Sure.
Yeah. So maybe a high-level question, right? So I think you mentioned that you aim at scaling this up eventually to treat the seawater. So what is the largest barrier or the field barriers that you can envision in scaling up this technology to treat large amount of seawater?
That's a great question. So I think one of the biggest barriers really is this phase separation because it's not an instantaneous phase separation. So if you have a very large volume of ionic liquid water mixture that you need to separate, you can heat the volume up, but the ultimate separation is just driven by a density difference, right? So we still are limited by diffusion of these two layers. So imagine if you have some ionic liquid on top that has to diffuse all the way to the bottom, which is where the ionic liquid layer is concentrated. So figuring out ways to really enhance the kinetics of that phase separation as we scale, or looking at different ways rather than doing it in a large tank to do it in a flow type of system where you're working with smaller volumes throughout the process. That to us is the biggest challenge because we've already tested the compatibility of the ionic liquid with the membranes. So we know that's not a challenge, but the biggest challenge will be getting the thermal separation to happen quickly enough so we can complete the cycle.
I see. So I think it's the idea that the salt will be more dissolved in the ionic liquid, so that the seawater can be treated with much lower salt concentration after this two-phase separation. Is that? That's straight ahead. I see.
Yeah, the salt gets removed in this membrane step. So the membrane itself blocks all the salt, right? So then we're left with a mixture of just water and the ionic liquid, which we can then do this thermal separation. So the intended application for this is not seawater, because seawater, reverse osmosis is designed to work very well with seawater, but this technology is really intended for applications where reverse osmosis is not suitable. So in a lot of cases with produced water from oil and gas, for example, reverse osmosis either cannot handle the higher osmotic pressures required, or the membranes degrade significantly. So that is where we would want to use a process like forward osmosis.
I see. Cool. So if going back to, still have like 2 minutes time for you. If going back to the previous one, you talked about this converting to this infrared emission, right? So you mentioned that this efficiency is already like high, like 91%. Have you studied like from materials selection perspective, right? So for this kind of a double layer membrane, right? So what is a high level rule to achieve high efficiency for such a design?
Yeah, so I think if we want to look at the full efficiency, we really should look at, it would be a combination of the absorber and the radiative coupling. So this factor of like 91 into the 70%. So that's only about overall 67% efficient. And one reason for that, as I mentioned, is we're using just a black body emitter rather than a selective emitter. And the reason for that is selective emitter design is non-trivial. So we've looked at some multi-layer designs that can be used, but we run into stability or degradation problems with those emitters over time. So like delamination of one of the layers. And so that's why we worked with just a black body emitter. But if we can design selective emitters to use for this lower material. So the selective absorber is working very well. It's this emitter. If we can design better materials which will emit in a much smaller window rather than broad black body emission, that way we could improve this efficiency further.